Okay. So we're down to 3. Okay. So let's talk about that net forces assignment. Okay. If anybody in Zoom land has any questions, type it into the chat box, and I'll kind of look for that. Okay. So here's the main idea. On any problem, you can come in here and go FAP, FOP, FNET. Okay? So the sooner you embrace this idea that you can set this thing up, the better off you're going to be. So if you look on even like number 1. So here's the semi, right? Okay, right? And we're moving along at 108 kilometers per hour, change that into meters per second. So when you hit the brakes, okay, there is no applied force. Okay, an applied force would come from like the engine or something to make it go forward. Your opposing force is just going to be that frictional force, which is also your net force. So it's only your net force that's equal to mass times acceleration. So you're going to find the acceleration using that equation, and then multiply that by the mass, and that's going to get you your frictional force. So that answer should be, on number 1, should be something times 10 to the 5th newtons. Okay, it's a big force. You're stopping a large truck. Okay. Then on number 2, then you're going to find mu, which is going to be force friction over force normal. Okay, force friction is your opposing force. That's what's creating that acceleration. So you're going to take that frictional force, right? You still have your test if you put it up in the tray. You just find it up there. So you're going to take that frictional force that you just found, divide that by the normal force. Now, if you want to, okay, this is just a little mathematical trick that you can do in this situation. Okay, it's purely up to you. I'm just going to show you a little bit of a shortcut. So force, go away. Force friction, you're going to find by taking mass times the acceleration. Okay, remember this is an absolute value. So you already found that acceleration up on number 1. Well, on a flat surface, force normal is the same as Fg, which is mass times your gravitational acceleration. So if you want to, you can shortcut this and just take a ratio of the acceleration that you found up in number 1 and divide it by 9.8 meters per second squared. Or you can find that force normal by taking m times g, and you can divide the whole thing out. Either way, you're going to get the same answer. So on number 2, that coefficient of friction should be a little bit less than 1. Okay? If you ever get a coefficient of friction bigger than 1, it's a train wreck. And that's an absolute value. Okay? Now, when you get to number 3, the whole key to number 3 is that it's at a constant velocity. So what that means is that if you look at FAP, FOP, and FNET. So if you want this thing to move at a constant velocity, your net force is going to equal 0. So here's the deal. On any problem, there's only 2 ways that any problem can play out. Either your net force doesn't equal 0, and you get an acceleration, which means your velocity time graph is going to have some kind of slope to it, up, down, positive, negative, something, okay? Or your force net is going to equal to 0, which means there is no acceleration, which means your velocity time graph is going to be horizontal line. Okay, literally. Those are the only 2 ways any force problem can play out. That's it. Those are the only 2 things. If you're at a constant velocity, make sure all the forces add up to equal to 0. If you're accelerated motion, they add up to a non-zero net force. So it might be positive, it might be negative. Okay? So on number 3, that coefficient of friction should be between 0.2 and 0.3. Okay? So find your frictional force, which is at 16.4, because that's how much force it took. So if you look on what's going to happen on number 3, that 16.4 newtons is your applied force. So the only way that this adds up to equal to 0 is if my opposing force is negative 16.4 newtons. Everything adds up to equal to 0. That's my force friction. Divide that by the weight of the block, there's your coefficient of friction. Now, on number 4, okay, on number 4, start with this box, fap, fop, finette. So here's the deal. You're told that there's an applied force of 18 newtons. Now, you can't find the opposing force if you tried, okay? I haven't given you the coefficient of friction. I haven't given you the value of the opposing force. There's nothing, you can't find it. You just have to assume that there is no opposing force. So that means all of that force goes to accelerate the box. So there's no mafia in this situation. There's no gravity because you're not throwing it up in the air. There's no friction mafia. You get to keep all the money. All 18 newtons goes to accelerate the box. Divide that by the mass, there's your acceleration. Now, on number 5, we changed the situation. We still have the same applied force of 18 newtons, okay? That's still there. Now, I gave you the coefficient of friction, so you're going to have to find that opposing force, okay? So to get this, you're going to go mu times force normal is going to equal that force friction. So that force normal is mg. So basically, it's mu mg is going to equal your force friction. Now, this is where you have to watch the sign, okay? This is where you have to watch the sign. If your applied force is positive 18 newtons, what's going to be the sign of your frictional force? Rachel?
Negative.
Yeah. And then the difference between those is going to be your net force. So your net force on number 5, the net force, should be around 10 newtons. Okay? So what that means is that of the $18 that you brought to this, you've got to pay about $8 of that to the frictional mafia, and what you have left over is the money that you get to keep. Now these are just round numbers, okay? These aren't exact, you have to calculate them. So you get to keep the 10 newtons, about, okay? It's about 10 newtons. So then you're going to take the 10 newtons and divide that by the mass to get your acceleration. Okay? So, your acceleration on number 7, okay, your acceleration on number 7 should be around 7 meters per second squared. That's an ish, but it's going to be somewhere around 7. Okay? So, what I'm looking for on number 5 is that you're going to have 2 different diagrams drawn to scale, and I want to see exactly what that scale is. So you're going to have Fg, Fn, that force applied, which is about 18 newtons, and then that frictional force, which is going to be about 8 newtons. Okay? So you're going to have Fn, Fg, I screwed that up. That's Fn. Gravity's acting down, your normal force is acting up. And you got about 18 newtons, and then you got about negative 8 newtons. So that's what the first diagram, drawn with a ruler on another sheet of paper, okay, and I see what the scale is. Then you're going to draw it tip to tail, and I always draw my gravitational force first, and then my force applied, my normal force, and then my force friction. So this gap is the net force, and that's what's going to allow this thing to accelerate. Okay? Everybody cool with everything so far? Good. Okay. There's only 3 of you, so, speak now or forever hold your peace. Now, on number 8 with the rocket, again, set up this FAP, FOP, FINET. So since this rocket is trying to get off the ground, what's going to be your opposing force? The frictional mafia or the gravity mafia? Huh? Yeah. So take the mass, multiply that by negative 9.8 meters per second squared, which you can get like negative 49 newtons. So you can have negative 49 newtons, which is your opposing force. You got an upward force of 129 newtons. The difference between those two is your net force. So there's your answer to number 8B. Okay? That's it. That's all you have to do. So you always, 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 always have to take gravity into account if anything's going vertically. The only time you don't have to take gravity into account is if I explicitly tell you you are in deep space and the effects of gravity can be ignored. Okay? Now, the other time you don't have to worry about gravity is if I took this tennis ball, and I'm not going to do this, okay? Let's say I'm going to throw it to Tina. If I throw it to Tina, when I let go of it, there is no other forces other than gravity acting downward on it. So if I just throw it like this, gravity is acting this way, and that's the only force acting on it. It's in the air, that's it, okay? Now, but if I throw it this way, while the ball is in my hand, the upward force from my hand has to be bigger than the downward force of acting on the golf ball, or otherwise I can't throw it up in the air. So if I'm going to make something accelerate upward, my applied force has to be bigger than my downward force. But as soon as it leaves my hand, I lose this applied force. The only force acting on it is gravity, which is going to create a negative force and a negative acceleration of negative 9.8 meters per second squared. Okay? So make sure on this one where you make a sketch of a free body diagram, so you should have 2 forces, your applied force and your gravitational force. You should have some velocity vectors drawn, and you should have an acceleration vector drawn. Okay, so that's what I'm looking for off to the side. Now, when you get to E, okay, when you get to E, you've shut off the engine, so there is no applied force. So that's like me throwing this ball up in the air. As soon as it leaves my hand, there is no force acting to make it move up in the air. The only force acting on it is gravity, which is going to make it slow down. Okay? So, because here's the most common misconception. As soon as it leaves my hand, everybody goes, oh, there's still an upward force making it go up. Inertia is not a force. Okay? Inertia is not a force. Inertia just says, hey, that ball just wants to keep moving up in the air because that's the velocity that it has. And since I observe it slowing down, that means that there has to be an external force acting on that golf ball. Okay? So, when you get to E, this goes away. This is your net force. Divide by that by the mass. You're going to get an acceleration of negative 9.8 meters per second squared, because that's the only force acting on it. Okay. And then make sure on E, you're going to draw 2 sets of graphs. On E, you're going to happen, and here's what I want labeled. This is like approaching on the way up and approaching once it starts to fall. So imagine here's this rocket, okay? So I want to know what's happening to the velocity vectors, the acceleration vectors, and the forces just as it's approaching the maximum height. And then once it starts to fall, I want a couple of velocity vectors, an acceleration vector, and a force vector. So on the way up, you should have 4 things. Velocity vectors, acceleration vectors, you should have 3 things. Acceleration vectors, velocity vectors, and a force vector. And then same thing on the way down. Velocity vectors, acceleration, force vectors. Okay? Anyway. Anything else you want me to go over? Zoomers, are you guys good? Okay. Hold on. Hold on. Hold on. So Joelle asked if she had to throw in the drag force on the rocket, and you don't have to. If I want you to calculate like the drag force on something going up in the air, I will tell you to worry about that. So unless I tell you to worry about like air resistance, don't worry about it. Okay? We're good? Going once, going twice? So, okay. So the lab that, well, I'm going to introduce today, and this is going to get a little bit dodgy because you guys are all off tomorrow. So we're going to start, it's like a computer simulation that has to be run on these laptops. So, I got to figure out how to do that. You guys will be back here on Friday when we actually run it. No, we're actually going to run it on Thursday. I might have you guys take a laptop with you. And that way you guys have those. But then there's half of you that aren't going to be here either. Okay, we'll figure that out later. Okay, so kind of the ultimate example of this whole idea is launching a rocket. So what I've got is like a video, and it's kind of old school because it talks about the space shuttle, but it doesn't make any difference. I mean, whether it's SpaceX, whether it's the Apollo missions, whether it's Mercury, Gemini, whatever it is, they all operate off of the same basic idea. So I've got a couple of videos to watch, even one of them is very long, and then I'll introduce the lab that you won't have to worry about tomorrow, but you're going to have to worry about on Thursday. So there's that. Okay, so let me get out of this. Okay. I got to switch over to that laptop. This is going to get complicated, so. Bear with me. And hopefully that works.
Ignition. Liftoff.
Over the past few decades, humans in spaceflight have proven to be some of man's most triumphant achievements. The underlying principles which made these achievements possible came as a result of hundreds of years of investigation into the behavior and structure of matter. It's these principles of physics which play the foundational role in making spaceflight a reality.
Is it going through those speakers now? Yes.
The launching of a rocket provides a spectacular display of force.
Okay. Ready to check on one thing. I'll be back in a second. And today suck. So I'm going to stop that for a second. Okay, Zoomers, we're back. We'll continue the video.
And energy. From a physics viewpoint, a rocket launch vehicle can be thought of as a large force machine. Its sole purpose is to apply a continual thrusting force in order to produce an acceleration. If the rocket is to achieve a low Earth orbit, the magnitude of the acceleration which is required tends to be quite large. The rocket must go from a state of being at rest on the Earth's surface to that of traveling 8,000 meters per second at some given distance above the Earth. This tremendous velocity change takes place over a relatively short period of time and necessitates the large amount of energy and acceleration provided by a rocket launch vehicle. The single most important component of a launch vehicle is the rocket engine. Use of a rocket engine provides the means by which thrust is produced in the vacuum of space. Since oxygen is not present in a space environment, an oxidizer must be carried on board the rocket along with the fuel. The Space Shuttle's propulsion system is made up of 5 different rocket engines, 3 main engines which use liquid propellant, and 2 rocket boosters which use a solid propellant. The tremendous temperature extremes which the Space Shuttle's liquid propellant main engines operate at required innovative engineering during their design. The engine's complex system of precision valves and pumps must handle the extremely cold propellants without freezing up. The liquid hydrogen fuel at minus 253 degrees Celsius is the second coldest liquid on Earth. However, when burned with liquid oxygen,
Okay. So, if you look at liquid hydrogen, and then for those of you that, is anybody here taking AP chemistry? Which is all three of the 3 of you? You're not? Slackers. Okay. So basically, if you're going to make something a liquid, okay, if you're going to take a gas and turn it into a liquid, you have to get it so cold that these particles, when they collide, they stick together. It's called van der Waals forces. So the coldest liquid on Earth is liquid helium, okay? So liquid hydrogen is the second coldest, because basically what happened is that hydrogen, because they're so small, they really don't want to clump together. So you can think of hydrogen as these really, really hyperactive second graders that don't want to stick together. But if you get the second graders cold enough, when they run into each other, they're going to stick together as a liquid. So the reason that they have all this expense of liquid hydrogen and liquid oxygen is because in the same volume of space, you can get a lot more molecules in there. So there isn't anything magic about it being, oxygen or hydrogen. The magic comes from it being but you have to get it really, really cold, so in that same space, you can cram a lot more molecules in there because it's so much more dense as a liquid than it is a gas. So, and here's the tough part of the engineering. So within the same system, you have to have the second coldest liquid on Earth, liquid hydrogen, and liquid oxygen. So those are really, 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 really cold. Then they're going to combine together in a violent explosion, and the temperature is going to be hot enough not to melt metal, but to actually boil it. So within the same engine, you have to have extremely cold liquids. They're going to explode and then produce something that's so hot it will make metal boil. That's the engineering challenge. Okay.
the temperature of the engine. This combustion chamber reaches 3,300 degrees Celsius, a temperature higher than the boiling point of iron. In the combustion chamber of the rocket engine, the propellants are consumed in a combustion reaction. The thermal energy generated from the combustion heats the newly formed gases to extremely high temperatures. These gases, possessing a large quantity of kinetic energy, subsequently go through an expansion of the rocket nozzle and are ejected at extremely high velocities. With the fuel being composed of liquid hydrogen and liquid oxygen, the hot gas which is expelled from the engine is primarily water vapor. The thrust which is produced by the engine can be explained in terms of Newton's third law. As the engine applies a downward force on the gases, causing them to be ejected, the gases must also apply an equal and opposite force, pushing upward on the engine. This upward force...
Now, here's what's important about this part. This is Newton's third law, okay? But here's what's important. This occurs within this engine. Notice that this doesn't require a surface to push against, okay? Yeah, you have a launch pad, and everybody says, oh, that gas is pushing down on the launch pad, and that's what makes the rocket go up. It isn't the force on that gas pushing on the launch pad. What makes it accelerate is when those gases are expelled they exert an upward force this way to counteract that downward force this way. So this is why rockets can operate in space. Because if the rockets had to push against something, like if it had to have a surface to push against, you could never have a rocket operate in space, because space is a vacuum. So when you look at how a rocket works, it's within the engine itself was where you have Newton's third law. It isn't these gases pushing on a surface and that surface pushing back against you. It happens within the engine itself. Okay.
Pushing on the rocket engine is essentially a reaction force to the gases being pushed downward, and is responsible for giving the engine its upward thrust. Newton's second law of motion, expressed in terms of momentum, can be used to find the magnitude of the thrust produced by a single.
Okay, now let's talk about this equation. So what's going to happen, what you guys are used to seeing this is, you guys are used to seeing mass times acceleration. You all are used to having the mass stay constant, and then this delta is change in velocity over time. That's how you all are used to seeing the force equation. Constant mass, change in velocity over time, right? Now, if you're talking about rocket engines though, and we'll get more into this when we get into momentum. If you get into rocket engines though, it's change in mass divided by time, and this V is the velocity of the escaping gas. So basically, if you want a really powerful engine, you want to consume a lot of fuel, which is this change in mass per unit of time, and then you want that fuel, that burnt gas, expelled at a very, very high rate of speed. So the more mass you can consume per second, and the faster you can get that velocity, that gas out of the back of the engine, the more force that you're going to generate. So this is why these rocket engines are so big. So big change in mass per unit of time multiplied by big velocity. That's how you generate force. Okay.
Single space shuttle main engine. With the propellant gases being ejected at a velocity of 3,600 meters per second, and at a rate of 470 kilograms per second, the resulting thrust generated by the engine is equal to 1.
So 470 kilograms per second is like a small car
As
per
summed by the
second.
second law,
So that's
the
how
greater
much
the
fuel
rate at
this
which
thing
the
is
hot
burning
gases
per
are
second.
exhausted, and the greater their velocity, the greater the resulting thrust will also be. Solid propellant engines make up a second group of rocket engines. These engines are much simpler in design due to the fact that they require no pumps, valves, or complex propellant feed systems. However, once ignited, they cannot be shut
Remember
down.
that. Once you light them, you
Solid
can't
rocket
shut them
boosters
off.
use a propellant which consists of aluminum powder as the fuel and ammonium perchlorate as the oxidizer. A rubber-based polymer binder is also added. This mixture fills the entire length of the solid rocket motor, except for a hollow channel extending through its center, which serves as a combustion chamber. When ignited, the propellant burns from the center out towards the sides of the casing at a nearly constant rate. An extraordinary amount of thrust is created.
Yeah, don't stand behind that
Propellant
engine.
gases are exhausted at a velocity of 3,300 meters per second and at a rate of 4,000 kilograms per second.
So 4,000 kilograms per second would be
Enough thrust
about
to
8,
maintain the flight of
about probably 10 like
747
big trucks per second. That's how much fuel is being kicked out the back. Okay, hold on. Now this is what I can never remember how to do it. Oh, come on.
The space shuttle system is the most technologically advanced and complex machine on planet Earth. Unlike the Saturn V rocket, which carried its payload to the moon, the shuttle is designed to attain a low Earth orbit. Achieving the necessary orbital velocity is no small task, as it requires the combined thrust of the shuttle's 3 main engines and 2 solid rocket boosters. With the large external tank storing the liquid propellant used by the main engines, and the 2 solid rocket boosters containing their own solid propellant, The total mass of propellant aboard the shuttle equals an enormous 1.7 million kilograms. This propellant mass accounts for 85% of the shuttle's total launch mass and provides 20
So
billion
basically, it's
kilojoules
a
of
flying
chemical
fuel
energy,
tank, is
which
all
is
it is.
necessary for attaining orbit. The filling of the liquid oxygen and liquid hydrogen tanks occurs on the launch pad several hours before launch. The oxygen vent arm, which caps the top of the external tank, allows vaporized oxygen to escape from the tank, and thus prevents the tank pressure from building up to excessive levels. A similar arm allows the lower positioned hydrogen tank to also be vented. As the final countdown begins,
The guy on the
flight
right
crew is taken to
is
the
a
launch
NASCAR
and
fan.
enters the orbit
Look at those
with the LEM
sideburns.
access arm. With all systems checking out in working order, the crew access arm is retracted at 7 minutes before launch. At 3 minutes before liftoff, the main engines are swiveled to their proper launch positions. All of the shuttle's engines are mounted on a pivot device, or gimbal, which allows the flow of exhaust gases and the direction of thrust to be controlled during ascent. The oxygen and hydrogen vent arms retract at just 2 minutes before engine ignition. At 7 seconds before launch, the sound suppression water system starts dumping 300,000 gallons of water onto the pad. This water is used to partially absorb the 170 decibels of acoustical energy given off by the engines, preventing it from fully reflecting off the pad and causing damage to the shuttle. Hydrogen igniters under the main engines are used to ensure that any hydrogen flowing out of the engines prior to ignition is burned off as it emerges. This prevents the buildup of a potentially hazardous cloud of explosive gas.
That would be bad.
At 6 seconds before liftoff, the 3 main engines are ignited. Shock waves coming out of the throats of the nozzles cause them to vibrate momentarily. At T-minus 3 seconds, the main engines reach 90% thrust.
Okay, so let's talk about this, okay? So there's a couple of things to consider. One, so these big solid rocket boosters are over here, okay? You've got these 3 big engines firing right here. But the rocket, the space shuttle hasn't taken off yet. So even though these engines are firing, why hasn't the space shuttle lifted off the launch pad?
Because there's not enough force yet.
Not enough force to do what? To overcome what?
Gravity?
Yeah. The gravity mafia is pulling down more than what these engines can provide. So what would happen is if you could grab a hold of the launch pad and pull it out, that space shuttle would actually begin to accelerate downward. Now, not like in free fall, okay? So it's kind of like, you know, here's my hydrogen balloon from yesterday, by the way, okay? If you watch that, this is how much hydrogen it's lost out of it, not even enough to stay up. So, but it's got a little bit of a buoyant force. So if I let go of it, okay, clearly the downward force pulling on this is more than the upward force from the balloon. I mean, this thing, even if I take this off, if I take off the binder clip, okay, there's not enough buoyant force to even like lift itself. But there's a little bit of buoyant force acting up. So this is what would happen right now, is if you removed the launch pad, that space shuttle would begin to accelerate downward. Not at 9.8, but it would begin to accelerate downward because the net force is pointing downward. It's bigger than the applied force coming from the engines. Now, the other thing that happens about why they start these first, because these are run off mechanical pumps. So if there's a problem with one of these 3 engines, you can shut them down and go, okay, hey, no big deal, let's try again. So they get these up and running first, and then they launch then they start those big solid rocket boosters. Because once you start the solid rocket boosters, you can't shut them off. So they're here, they're firing these, making sure everything's cool, and then they fire up the big boys on the outside.
½ second before liftoff, the solid rocket boosters are ignited as explosive hold-down bolts are triggered. During the initial part of its ascent, the shuttle's engines deliver a combined power of over 100 billion joules per second, an amount of power which is equivalent to the output of 85 Hoover dams. A distinction can be made between the different types of engine propellant, as the main engines are observed to burn with a clean light blue flame as a result of the hydrogen and oxygen combustion. This contrasts with the solid rocket boosters, which burn with a bright orange flame due to the combustion of the solid aluminum fuel. The dynamics of the launch can be studied in more detail by examining the forces involved during the shuttle's ascent. With the three main engines ignited and applying their combined thrusting force of 5 million newtons, the shuttle still remains motionless. At this point, the upward thrusting force represents only a fraction of the total shuttle weight, which is equal to 20 million newtons. If the supportive launch pad was taken away during this period, the net force would cause the shuttle to accelerate downward. In order for the shuttle to accelerate upward, the total thrusting force must be greater than the shuttle's weight.
Now,
This
look
takes
off to the
place
right
when
when they
the
start
solid
this
rocket
long
boosters
rocket booster. See all that stuff blowing out
With
there?
the two solid rocket boosters applying an additional 26 million newtons of thrust, the total thrust from all engines is now 31 million newtons. At this point, the net force is directed upward and the shuttle lifts off. The initial upward acceleration can be determined by using Newton's second law of motion. With a net force of 11 million newtons,
Okay, so here's the heart and soul of this, okay? This is the absolute heart and soul of what you have to understand. You have an applied force of 3.1 times 10 to the 7th newtons, okay? That's the total upward force between these two solid rocket boosters and these three engines right here. So that's your total upward force. The downward force, which is what the gravity mafia has to be paid off, is negative 2 times 10 to the 7th newtons. So the difference between these two is your net force. This is what's left over to actually accelerate the rocket engine. So you take that and you divide it by the mass, boom, there's how you get your acceleration. Now, an interesting thing happens with rockets, though. This number is pretty much going to stay the same. You can adjust it a little bit, but your applied force pretty much stays the same. But this is where it gets interesting. As this thing burns fuel, what happens to the weight of the ship?
It gets lighter.
Yeah, it's going to become smaller and smaller and smaller. So I'm going to have the same applied force, but I'm going to have a smaller and smaller weight, right? So what's going to happen to my net force? Tina, what's going to happen to my net force? What'd you say? Did you say be bigger? Yes, it's going to be larger. So here's an interesting thing, though. So I'm going to have a larger net force, right? So this number is going to get bigger. But what's going to happen to the mass that I divide by? It's going to become smaller. So what happens is that my acceleration actually, if you look at like an acceleration time graph, the acceleration time graph is actually going to be a quadratic function. Where you're, not only are you accelerating, but stay with me here, my acceleration is accelerating because I'm ending up with a larger and larger net force that I'm continuously dividing by a smaller and smaller mass, which is actually going to make my acceleration go bigger and bigger and bigger. Okay? Makes sense. Okay.
acting on the total shuttle mass of 2 million kilograms, the initial acceleration is equal to 5.5 meters per second squared. With the thrust initially remaining constant, the shuttle's acceleration will continually increase as the engines expel their propellant and reduce the mass and weight of the shuttle system. With 9,400 kilograms of propellant being exhausted every second, the shuttle's mass becomes reduced very quickly. After only 30 seconds into the flight, the shuttle is traveling with an instantaneous velocity of 200 meters per second.
So that's about
At
two-thirds
this
the speed
point,
of
the
sound.
engines have already expelled 280,000 kilograms of propellant, reducing the shuttle's total mass and weight by 14%. Newton's second law of motion shows that the acceleration has now increased to 8.2 meters per second squared. At approximately 50 seconds into the flight, the shuttle enters a critical period during its ascent as its velocity approaches the speed of sound. As the shuttle moves through the atmosphere, it creates a disturbance in the surrounding air. The resulting pressure waves spread out in spherical shells at the speed of sound. As the shuttle approaches the speed of sound, it begins to catch up to the pressure waves it produces. With the distance between wave crests becoming successively smaller, the waves begin to pile up in front of the vehicle, creating a wall of high pressure. This pressure barrier, sometimes referred to as the sound barrier, presents resistance to the shuttle's motion. Breaking through this pressure barrier creates a period of maximum dynamic pressure.
That was actually one of the
and
things
results
for a
in
while, we didn't know if we
considerable
could
amount
break
of
the
aerodynamic
sound
stress
barrier,
being
that's why it was
imposed on
called
the
the sound
shuttle.
barrier, because they thought like.
To
it was
minimize this stress, the shuttle
impenetrable.
throttles down in an effort to reduce its acceleration at the time of passage through the pressure barrier. After breaking through the barrier, the pressure becomes greatly reduced, and the shuttle's motion is no longer impeded. With the shuttle no longer experiencing a high level of aerodynamic stress, its engines are throttled back up to 100%. Now, traveling faster than the speed of sound, the shuttle outruns the sound waves it produces. The resulting pattern of waves leads to constructive interference taking place, where successive wave fronts overlap, forming a single very large wave front, which carries a tremendous amount of sound energy along with it. This large wave is called a shock wave, and forms a conical shell of sharply increased pressure with the shuttle at its apex. Throughout the remaining atmospheric portion of its ascent, the shock wave will continue to trail behind the shuttle. After 100 seconds into the launch, the engines have expelled an enormous 940,000 kilograms of propellant, reducing the shuttle's total mass to almost half of what it was at the time of launch. With this decrease in mass and resulting increase in net force, the shuttle's acceleration has climbed to 18 meters per second squared. During this period of time, frictional heating caused by the atmosphere reaches its maximum level, as collisions with air molecules cause
Oh, I
portions of
hate
the shuttle's
I hate air
exterior to
molecules.
reach
My
temperatures of
God,
1,000
stop.
degrees Celsius
There's
for
no
a
such
short
thing
time.
as an air molecule.
At 2 minutes into the flight and at an altitude of 45 kilometers, the two solid rocket boosters have consumed nearly all their fuel and no longer provide thrust to the shuttle. At this point, the shuttle's weight can be considerably reduced by dropping the spent booster casings. The boosters are released by explosive bolts and are then powered outward and away from the shuttle by 4 small separation motors on each end of the solid rocket boosters. The reusable booster casings parachute back to Earth, splashing down in the ocean with an impact velocity of 18 meters per second. With the solid rocket boosters no longer present, the total amount of thrust acting on the shuttle dramatically drops. During the initial part of the vehicle's ascent, a large portion of the 31 million newtons of thrust was primarily used to accelerate the enormous mass of
See,
propellant.
it becomes like a
aboard the shuttle.
catch-22. Oh, we need bigger
With most of that
rockets.
propellant
Well, bigger
now
rockets,
consumed,
way
and the
more.
shuttle's mass
So
will be
then
one
you have to
third
have a
of
big,
what
because
was
that's,
at launch.
more of a
The thrust
force to
provided by the
overcome
3
it.
main engines is sufficient to maintain the vehicle's acceleration. At 8 minutes into the flight, the shuttle's velocity has increased to 7,000 meters per second, a velocity more than 20 times greater than the speed of sound. During this time, the acceleration approaches 30 meters per second squared, a value which is 3
So
times
what that means
greater
is that
than the
you would feel like
120
3
meters per second
times
squared
heavier than you do
gravitational
right now.
acceleration
So
experienced
if you're
at the
used
Earth's
to lifting
surface.
your arm under 1G, your
The
arm
crew
would feel
aboard
3
the
times
shuttle,
heavier
the
when you go to
acceleration
lift it.
of 3 Gs forces them back into their seats as they feel the sensation of increased weight. Although the acceleration causes some discomfort and stress to the body, it is less than half of what was experienced by the Apollo astronauts aboard the Saturn V rocket. Cutoff of the main engines occurs at 8.5 minutes into the flight, at an altitude of 120 kilometers above the Earth's surface. 12 seconds after main engine cutoff, the near-empty external tank separates from the shuttle. At separation, a small valve in the nose section of the external tank is opened, allowing pressurized gas from the liquid oxygen tank to escape. The escaping gas applies a rotational torque to the tank, causing it to slowly spin. This tumbling motion prevents aerodynamic skipping off the atmosphere and ensures the correct re-entry trajectory.
Because if it wasn't spinning, it would
As
act
the
like
tank
a
breaks
rock
out upon
that,
re-entry,
that hits
debris
on
will
water
lose
and
the
skips
impact
off.
of the pre-flight
So by
rotation
making it
in the
spin like
ocean.
that, it's going to burn up in the atmosphere.
With the external tank gone, the remaining orbiter represents only 5% of the shuttle's original launch mass. Having spent all of its main engine fuel, the shuttle's orbital maneuvering engines provide the final thrust for orbital insertion. The maneuvering engines, along with the other engines which are used while in orbit, use a hypergolic propellant. Hypergolic propellants are fuels and oxidizers which ignite spontaneously on contact with each other and require no ignition source. This easy start and restart capability makes them reliable and advantageous for engines which are used a number of times while in orbit. At 10.5 minutes into the flight, the two orbital maneuvering engines fire to place the vehicle in a low elliptical orbit.
Oh, hold on. Oh, I stopped.
The engines provide a total thrust of 53,000 newtons, giving the 95,000 kilogram orbiter an acceleration of 0.56 meters per second squared.
Okay. So this is how orbits work. If you were to stop the space shuttle right now, all it would do is just fall to Earth. So what happens is that because of Newton's first law of motion, this space shuttle at any given instant wants to fly off in a straight line. But what's happening is that the gravitational force is making it continuously fall around it. So if this thing wasn't going fast enough, what it would do is it would fall in like this. If it was going too fast, it would go into these big elliptical orbits. So the only way this thing stays in orbit is there's a gravitational pull acting this way, which keeps this thing in a state of free fall. So the only way you can orbit is if you cannot orbit in zero gravity. You have to provide the downward force to keep this thing traveling in a circle like this. Because without that gravitational force, it would just fly off in a straight line.
The final step in achieving the desired orbit comes at 45 minutes into the flight, as the orbital maneuvering engines fire for a second time, placing the shuttle in a nearly circular orbit at 400 kilometers above the Earth's surface.
And we'll do all that math later. Okay, we got one last one to watch. And this is what you're going to do in the lab.
Sending a manned spacecraft to another planetary body presents an enormous scientific challenge. That challenge is immeasurably escalated by having to also return the manned spacecraft safely to Earth. The extremely successful Apollo missions made a total of 6 different manned landings on the surface of the Moon. The lunar module, consisting of a lower descent stage and an upper ascent stage, allowed the astronauts to descend from lunar orbit and set down on the Moon's surface. This vehicle was a true spacecraft in that it was capable of operating only in the space environment. Having used its descent engine to land on the Moon's surface, the lunar module would be required to do what had never been done before: lift off from a planetary body other than Earth. Due to the extremely different physical characteristics of the lunar environment, the dynamics of launching a spacecraft from the Moon's surface greatly contrast the dynamics of an Earth launch. The black sky during the daytime bears witness to the fact that the Moon possesses no atmosphere to scatter sunlight. Because of the lack of
That's
any
why
atmosphere,
our sky is blue,
stress and
because
frictional
it
drag are
scatters
non-existent
moonlight
during
as
the
it
launch
comes
from the
in.
Moon's surface. In contrast to Earth launches, streamlining of the spacecraft becomes unnecessary, as the lunar module's protruding components in a non-streamlined configuration is of a functional design and presents no problems during launch. In order to provide the thrust required to lift off from the surface and attain lunar orbit, the ascent stage of the lunar module possessed a single rocket engine. Because there was no backup engine and no other means to lift off from the Moon's surface, a malfunction could absolutely not be tolerated. The single engine had to work. The engine used the most reliable propellants available, hydrazine and nitrogen tetroxide, two compounds which spontaneously ignite upon contact with each other. Because the gravitational acceleration of the surface of the moon is only 1.7 meters per second squared, the 5,000 kilogram ascent stage has a weight of only 8,500 newtons, a weight 6 times smaller than that which it would have had on the surface of the Earth. Because mass remains constant throughout the universe and is not affected by gravity, the spacecraft's 5,000 kilogram mass requires the same definite amount of net force to achieve a given extent.
Okay, now, here's what I want you to, what they just said. That thing has a mass of 5,000 kilograms, okay? And this is the numbers that you're going to use on the lab that you're going to do today. If you're on the moon, that thing has a mass of 5,000 kilograms. If you're on the Earth, it has a mass of 5,000 kilograms. Because it's a measure of how much stuff there is. Now, on the Earth, you would take 5,000 times 9.8 meters per second squared, and you would get like negative 49,000 newtons. So if you're going to try and get that thing off the Earth, you would have to apply a force greater than 49,000 newtons to make it accelerate upward. If you're on the moon, where g is like negative 1, or the acceleration due to gravity is negative 1.7 meters per second squared, then you're just going to take 5,000 times negative 1.7, and you're going to get like around negative 8,000 newtons. So on the moon, even though it's the same mass, to get that off the moon, you only need about 8,000 newtons of force. On the Earth, you need about 50,000 newtons of force. Okay? So that's why it's easier to launch from the moon than it is from the Earth. It isn't because there's less mass. The mass is the same. The inertia is the same. But the gravity mafia on the moon is a lot weaker. Okay, so what you're going to do in this lab, okay, so we're done with that. So here's what's going to happen tomorrow. Okay, well actually, you guys are going to start crunching the numbers and I'll get you the data. Here's what everybody else is going to do tomorrow. So, because this only exists on these laptops, because these are the only laptops that have this program on it. So, what you're going to do, this is, you're trying to land this ship on here. So, what's going to happen is that you're going to keep track of a whole bunch of things. Your horizontal acceleration, going this way, your vertical, your horizontal velocity, or Vx, your vertical acceleration, your vertical velocity, the value of the main thruster, that's the applied force. Okay, this is going to be important. The value of the main thruster is the applied force. So, this thing has a mass of 5,000 kilograms. You're going to multiply that by negative 1.67 meters per second squared. And you're going to get a downward force of negative 8,350 newtons. So, that is always working against you. The gravity mafia always has to be overcome. So, if you're going to accelerate upward, this force has to be bigger than 8,350. If you want to have a negative acceleration, that force is going to be less than this. So, this whole lab is brought to you by the idea that FAP plus FOP equals phonetic. Now, horizontally, there's no vacuum, it's a vacuum on the moon. So, horizontally, the only way that you can make this thing accelerate horizontally is to fire these side engines, okay? Because there's no external force. So, if you get it moving, this is like that frictionless hockey puck. Once I turn on the jets for that frictionless hockey puck, if I give it a push, it's going to maintain whatever velocity it has horizontally. But if I push that thing and it flies off the edge, then it's going to accelerate because now there's a vertical force acting on it. So listen to me. Horizontally, you can use force net equals FAP plus FOP. Horizontally, there is no opposing forces because there's nothing here. You only accelerate horizontally when you fire these engines. Vertically, there's always the gravity mafia that you have to worry about. So what you're going to do is that you're going to hit launch. Let me clear this out. So you have to land with a velocity less than -1 meter per second. Stuck it. Okay, this is what I do. I just it's like I'm grading papers. Okay, so what you're going to do is that I'm going to have to give you that data. That'll make sense once you look at the lab. But so what happens is that notice that I had a horizontal vertical velocity, but I didn't have any horizontal acceleration because I wasn't firing the engines. I had a positive acceleration of 0.01, and I got a negative velocity of -0.42. So in this program, anything going down, displacement, velocity, acceleration forces, is a negative value. Anything going to the left is a negative value. Anything moving to the right or up is a positive value. So this is why you notice here, notice that my applied force is 8,400 newtons, okay? I have a positive acceleration. So that means that my applied force is a little bit bigger than the weight of the ship. That's why I've got a very small positive acceleration. Now, if I go back, down here in this bottom left corner, there's like a little scroll bar that you can move back and forth. So if I move that back, okay? So now, look at this. The value of my main thruster is 7,400 newtons. So that's less than the weight of the ship. I've got a negative acceleration, so that means I've got a negative net force, and I've got a negative velocity. So what's happening here is that I have a negative acceleration, I've got a negative velocity, so vertically I'm speeding up because these two values are the same. So on my velocity time graph, I'm in a negative velocity, and I'd have a negative acceleration, so I'd be speeding up. Okay, got the idea. So, let me hand out the lab. I try to be organized. Oh. Where did that go? See, I tried to put stuff away, and if I just let everything lay out. There it is. Okay. So here's what's going to happen. So what you all out in the studio audience, okay, and you guys need to have done by Thursday, okay, so here's you have until Thursday to do this, is that I want page 1, and the front and back of just page 1 done by Thursday. So up here in the top, I've given you all the parameters. The gravitational acceleration on the moon, -1.67. Mass, 5,000 kilograms. Left and down is negative, up and right is positive. So, just like NASA isn't going to turn you loose unless you can understand basic Newtonian mechanics, neither am I. So, what you want to have done is have the front and back done by Thursday. And then on Thursday, you all are going to either zoom in or watch the video of your classmates trying to land the ship. Okay? And then over on page the second page, this is what I'm going to send you guys some data from theirs, okay? And then what you're going to do is you're going to verify if the program is actually working. So what I'm going to do, I'm going to give you like an acceleration, like I would give you this AY negative 0.19. I would give you this VY negative 0.04, and I'd give you the value of the main thruster. So then what you're going to do is use that information to calculate the net force. Okay, so you're going to go FAT, FOP, FNET. So this would be 7,400. You subtract 8,350, which you'll see is the weight of the ship. The difference between those two is your net force, which is going to go here. You're going to divide that by the mass of 5,000 kilograms, and hopefully that acceleration is negative 0.19. You're just trying to verify that the computer program is working like it should, okay? And then you're going to tell me if it's speeding up or slowing down. Well, look at this. If I gave you this where you had a negative acceleration and negative velocity, what are you doing? Speeding up or slowing down? Rachel, speeding up or slowing down?
Speeding up.
Yeah, because these would have the same sign. And then I give you another set of data, and then you do that. So I will email your group the data that you're going to need for here. And then after that, you're going to answer the rest of these questions. So this is going to be due on Friday. Okay? So everybody's going to, you have nothing to worry about tomorrow unless you just want to work on this. But I won't give you anything else tomorrow. There's no videos to watch. There's nothing for tomorrow. Okay? It's just you want to have this done by Thursday so that way I'm trying to figure out how I can verify your guys'. I'll just have to verify your answers on Friday when you guys come into class. So I'll look at your answers on Friday when you guys come into class. But I'm going to send you the data and you can do that second, so you can have that done, and then I'll look at this on Friday when you guys are in class. Let's just do that. And then we got a lab to do on Friday. You guys will collect that data. So, okay, that's the story. So, all right, kids, we're done.